This is part 2 of the empirical and quantitative skills assessment. Originally, I planned on having it all as one, but it cut off. So the previous one, part 1, with this assignment, it's multiple pages. And so part 1 dealt with pages 1 through 3. So this will continue on now with picking up basically on page 4. So with the previous work, what had happened is it was describing, we took Pseudomonas aeruginosa bacteria and it had been grown, and then we took aliquots or little samples of it and read it in a spectrophotometer. We used the wavelength at 600, so that will measure bacteria. So 600 nanometers. And what we had found from the previous work was that when we get an absorbance reading of 0.892, that correlated to 147,000 bacteria per mil. Now, I just, in the example, was just using this number. Okay, you're probably going to get something a little bit different, but I was just throwing the 147,000 out. So just to keep the numbers the same for that, you have to actually calculate that number. That's where you put the sample in the spectrophotometer, and you got this number right here of the 0.892. That came from the machine. It read it, and that's the number it gave you. How did you get the 147,000 or whichever number you got? This was from plating. Remember, you diluted the samples out and then you plated them, and you actually counted the number of colonies on the plate, between 30 and 300, and then you multiply that by the dilution factor, and that's how we got this number. And so you always have to, initially, whenever you start with a new media, or the first time you ever do this, is you have to not only get your measurement from the spec, such as the 0.892, but you have to be able to plate out your sample so you can correlate what does that number mean. And so now what we're moving on to is on page 4, and there's a graph. And so I will attempt to, it's not wanting to draw. Here we go. Draw a graph. Here we go. On page 4, there's a graph that is drawn where they have taken several readings from the spectrophotometer, and it roughly looks like this. It was over a time period of hours, so down here is your hours. They went through 12 hours. Over here is, it's called the OD 600. So once again, you're still measuring on the spectrophotometer. And whatever number it is at time period, you plotted that number. And this is very similar to what you may see with a growth curve for bacteria. You get the log phase, you get the stationary phase here. Apparently the first reading that they took, it was already, as you can see, as it's starting up, it was already in log phase. And what it is asking you is it's saying, okay, so let's just say at a particular time period, and your axes are going to be labeled, but let's say at whatever particular time period, we want to know at this time period how many bacteria were in that sample. Well, all you do is okay, this is not a straight line because I can't draw, but go straight line up here to where it meets the line. Now come over here, and what number do you have here? Which on the graph it's actually written right here. So you're going to have a number. How are you going to figure out the absorbance? This is the same thing that you did previously. Let's just say that the number that you see from the graph, let's say that number is, and I'm just going to make up a number here because I'm not going to give you the actual answers on the assignment, but let's just say it's 2.973. And you're like, okay, that's the absorbance reading on the spectrophotometer. So how am I supposed to know how many bacteria were there? That's where you go back to your original formula from the previous pages. You take the 147,000. That's your bacteria per mil, or your CFU per mil. You're going to take this number, you are going to multiply it by 2.973. There is a point right there. And you're going to divide that by the 0.892. Where was the 892 from? That was the original number where you got the 147,000. And then the number that you get from that, which if those were the numbers you actually had, once again, my little handy dandy calculator. Then the answer would be 4, 8, 9, 9, 4, 5 bacteria per mil. And once again, the way to kind of check yourself, 489,945 is larger than 147,000, which makes sense because the OD was much larger. 2.975 is much larger than 0.892. So once again, it's a way of kind of double checking yourself. So that's how you would calculate what is the population density. On page 4, it's asking you, the first question is at 8 hours on this graph. Then it's going to ask you to figure out the generation time. To figure out the generation time, what you would do is, let's move to a new slide, get you a clear picture now. So now, remember, there's a formula you can use, but I just find it easier. When you look at your standard growth curve here, what you're going to look at for your, on the growth curve, when you're figuring out generation time or doubling time, remember that's the number of where it doubles. Look here in your log, that's your log phase. That's where you're going to be looking at to figure that out. Stationary phase, remember that is now where, and to show, let's see, a different color. Oh, let's just go with black. Stationary phase is where it starts to plateau out. And then death phase is down here where it starts to decrease. So, Pseudomonas aeruginosa is commonly found in the soil, and so it has a wide temperature range it can grow at. It kind of grows everywhere, but it's commonly found in the soil. Can it also grow at 37 degrees Celsius, which is 98.6, that's our internal body temperature? Yes, it can. It can cause several different types of infections. If it's allowed to penetrate, it's an opportunistic organism. But naturally it is found in the soil, which is a little bit of a cooler temperature. So just kind of keep that in mind. There are some additional questions on both pages 4 and 5. One has to do with the death phase. On the initial graph they show you, there is no death phase, and it's asking you why. Think about what happens in a growth curve when a cell does reach death phase. Why is it going into death or decline phase? What's happening to the nutrients at that point in time? So, and also keep in mind, No, in my lectures, I talk about the fact that when you're looking at a typical growth curve, when you have an organism that is typically in log phase, where it's growing very rapidly, so in this phase right here, it's growing very, very rapidly. From an industrial microbiology standpoint, if you are trying to purposely produce a product, you want your cells to stay in log phase. You want to have that rapid growth occurring, that quick doubling time. And if this is where you start putting all the pieces together of what you have previously learned. When you first were introduced to metabolic reactions, etc., one thing we talked about was feedback inhibition. That is where the product that's being produced becomes an inhibitor and will actually turn off the reaction, which makes sense. You need to make product A. Well, when you start building up a lot of concentration of product A, you don't need any more, so have product A turn around in the step 1 and shut things off. Okay, we got a lot of product A, we don't need any more, turn it off. But in an industrial setting where you're wanting to produce product A and you want a lot of it, because you're probably trying to sell it, you don't want it to shut it off. So what you do is you have your organism produce product A, but as soon as product A is being produced, you pull it out of the media. You remove it from that environment. That way the concentration never gets high enough where it's going to shut down the process. And so if you're constantly removing that product, that means your bacteria are going to continue indefinitely to make product A, which then in turn, like I said, you're going to probably sell. So that's the way you're kind of forcing your organisms to stay in log phase. Provide them more nutrients, remove the product, so they can just keep making nonstop the product that you need. So like I say, from an industrial standpoint, we want to keep our organisms in log phase. You don't want them going into stationary, or certainly not death phase, because then A, you're not going to get your product. You're going to run out of the product. What's happening with that organism when it goes into death phase? Just kind of think about that relative to nutrients. So that's just kind of a quick explanation with this worksheet. And like I said, this one, you need to watch the first part first and then watch this, otherwise this won't make sense. But good luck with it.